So, we will now hear a short series of lectures that will offer us a glimpse into Leslie's rich and inspiring scientific journey, which continues to yield remarkable discoveries on the theme of crystals in all dimensions, the title of today's event. So, on behalf of the organizers and Leslie, I apologize to all those who wish to share their words with us today, but due to time constraints, were unable to be invited to the stage. Now, I would like to introduce our first speaker, Professor Lia Addadi, who did her PhD with Meir Lahav, and she is our first very distinguished speaker. She warned me not to go into details about her prizes, so I'm a little bit, I'm trying to be careful. So, Lia, this cannot be taken from you. You have inspired us with groundbreaking revelations on the formation, shapes, function, and control of crystalline material in nature. So it is my honor to invite you, Professor Lia Addadi, to share with us your story on looking at crystals with Les, from chirality to biomineralization and atherosclerosis. Thank you, Lia.
Thank you for not embarrassing me too much. When they ask me how should I introduce you, I say, just say that I'm a nice person. It will be, that's enough. Thank you. So, it is quite impossible in 20 minutes to give you a complete picture of all the works that we have done together with Leslie in almost 50 years of working together and collaborating, especially because during time, we shared work on 4 different subjects. First on chirality, and then on biomineralization, and on biogenic photonic crystals, and in cholesterol. And I counted, we have published together 58 manuscripts. So I decided just to choose 1 or 2 manuscripts for each section that represent some highlights of what we have done together, and to give you a kind of idea of what I'm talking about. And the first manuscript that I chose about crystals and chirality is a link between macroscopic phenomena and molecular chirality, crystals as probes for the direct assignment of absolute configuration of chiral molecules that we wrote together with Ziva Berkovich-Yelin and Isabella Weisbuch, of course, Meir Lahav, and Leslie. And this was published in 1986, but it summarizes work that we had done starting from 1980 about. And it is particularly dear to me because we spent months with Leslie, Leslie and I, sitting in the seminar room in the 4th floor, and discussing a couple of hours every day, writing and discussing. So what are we talking about? These are the hands of Vered, Leslie's daughter, and they represent chirality because, as you probably, almost all of you know, the name chirality comes from keria, that is hands in Greek. And what characterizes hands is that the right and left hand are not superimposable. In order to relate one to the other, we have either to have a mirror plane or to have a center of symmetry. And they are not there. So we are talking about symmetry, and you know, that's why I chose this one today. So we are all on the same type of notes. And what is the problem now? The problem is that conventional X-ray diffraction cannot distinguish between a crystal built of right molecules, R, and the crystal built of left, that is S, sinister molecules, the left hands. And then this problem is essential both fundamentally and practically, because we want to know what is the spatial configuration of all the asymmetric molecules that form our body and are in our environment. And this is a problem that was solved by Byfoot in 1951. It was independently confirmed only in 1973, and we provided an alternative solution in 1980-81. So it's less than 10 years after the problem was solved. And what did we do? You see, we were interested at the time in crystal growth, and this crystal is made of small men. And the small men are all identical. The color only represents their position in the crystal and the symmetry, and they are chiral, right, and sinister and left. And the additive, the tailor-made additives are also chiral, and you can see that the little man with the hat that is right can enter this crystal taking the position of the white and of the green man only if it comes from above, because if it comes from below, the hat bothers it and it cannot enter. And the same, the opposite. For the S1, it can enter only from below because from above the hat disturbs it. But when it grows, it enters the crystal, then the hat bothers the growth of the crystal because the next molecule bumps into the hat. And in this manner, the crystal growth is affected and the shape of the crystal changes. Now, it is for this reason that actually in glycine, that is a symmetrical crystal, the R little man amino acid can enter only from above, the S only from below, and so we obtain crystals that have shapes that are opposite to each other. Now, we were discussing this issue with Meir, as it often happened, and we got very excited because we said, all right, now if we can do that, then we can know in the crystal where, in the symmetrical crystal, where sits the right and where sits the left. And then we ran very excited to Leslie, and we told him, and Leslie looked at us as if we were completely crazy and said, but in a symmetrical crystal, I know very well what is the right and what is the left. And this is because when both hands are there, then this situation is very different from this situation. And these are again the hands of Vered, demonstrating the issue. And so we suddenly realized that in fact we had a way to directly assign the absolute configuration of chiral molecules depending on the effect that they had on the symmetrical crystal of glycine, and this is Isabella Weisbuch that did, the first author of the work. All right, then time passed, and in the meantime I started to collaborate with Steve Weiner on biomineralization, and we were very interested in these complex shapes of crystalline structure in organisms that still appeared to be one crystal, notwithstanding their complex morphology. And then we went to Leslie and we asked him to help us to understand how this may happen. And indeed, it came out that these are single crystals. Some of them are more perfect, some of them are less perfect, but they are all single crystals. And not only that, but the shape of the crystals is controlled by introducing anisotropy in the crystal texture and consequently in the crystal growth. And this reconnects to the thread to what we are doing before with chirality and reduction of symmetry. And in fact, after Amir Berman, Jana Eisenberg started to study these crystals and crystals of sponges and the reduction in symmetry in the texture of the crystal. And the extreme case is this one, in which we have just one crystal. This is the spicule of a sponge with 3 arms, and each arm grows with a different texture that matches and determines the shape and results in a global reduction of symmetry. And again, we reconnect to the beginning of our collaboration. And then in the third subject, the biogenic photonic crystals, there are many crystals in organisms that fulfill optical purposes. For example, the iridescence of fish scales or in the eyes of many sea creatures. And the eyes of decapod crustaceans, such as the crayfish, are built in a manner that is quite similar in principle to the eyes of the fly, where hundreds of square units are lined with mirrors that concentrate the light onto the retina. But there is another reflector that is called the tapetum reflector that sits here, whose task is to collect the light and scatter it back, the light that was not that was missed in the first pass, and reconvey it to the light receptor. Now, this scattering effect is achieved through these incredibly organized spherical hollow particles that are made of single crystal subunits that you see here. And in fact, their structure was optimized, is optimized, and their packing is optimized for maximum performance in light scattering. That is their function. But the issue was, what are the crystals made of? They are made of a material that's called isoxanthotherine, and we wanted to understand why this material, not something else. But the crystal structure was not known. And so Anna Hirsch together with Leslie, of course, and with Lia Addadi, they made their magic and succeeded in predicting the structure of the crystal without any knowledge from basic symmetry principle. And then this was optimized by density functional theory and validated by comparison with experimental data. And this was not done only for this compound, but for a number of other compounds that fulfill optical purposes. So we finally got to an analysis of what are the characteristics of the crystals that form photonic structures in the eyes of organisms together. And this is a paper that was just published 2 weeks ago with Leslie, of course, and Steve Weiner, Lia Addadi, and Dan Oron. And what we understood is that there are 4 levels in the control of the optical properties. One is the molecule, then the second level is the crystal structure that induces the right parameters to get optical activity. The third level is the crystal morphology that allows the light to penetrate from the appropriate direction. And the fourth level is the superstructure that permits to the light to be treated and reflected as to fulfill its function. And this, I think, is a fantastic type of operation. But we go on, and in the same period, more or less, that we started the photonic crystals, we started also to collaborate on the cholesterol crystals. Now, this is a problem that, unfortunately, many of us deal with. Cholesterol is essential in the cell, and because it controls the fluidity of the cell membranes. But when it goes crazy and the so-called bad cholesterol, the LDL, enters the wall of the blood vessels, as a result, finally, cholesterol crystals may form, the arteries may become clogged, and this gives us atherosclerosis and a lot of problems. When, where, and how cholesterol crystals are formed is not clear. Now, Hanna, Rapaport, and Dina Salomonov, who are both here, together with Leslie, discovered a new structure of cholesterol crystals that was unknown, first from thin layers at the air-water interface, and then from multi-layers, and the work was optimized and completed with Rita Shepelenko and Lia Addadi only a couple of years ago. And this new structure of cholesterol became much more important than what at the beginning one may have thought. Roy Ziblatt, working with me on cholesterol crystal formation in the cell, showed that in artificial membrane bilayers, when cholesterol is above a certain level, it forms two-dimensional domains that are crystalline and have the structure that was newly discovered. And then Netta Versano showed that the same can happen in cell membranes, and crystals of cholesterol may nucleate and form on the membranes. But beyond that, Netta saw that in certain cells, the cells that eat the bad cholesterol, the LDL, she noticed huge crystals that spear the cells, and we couldn't understand what these are until we discovered that these are in fact helical crystals. And the helical crystals have the new structure that was discovered a few years before. And then we remembered that also in another pathology, that's gallstones, in 92 still, Freddy Konikoff showed that helical structures are formed, and Ishi Talmon from the Technion showed that the helical crystals in bile that formed the gallstones eventually have the same new monoclinic structure that was discovered by Leslie. And last but not least, this appears to be relevant also to atherosclerosis, because Jenny Kapua-Shankar showed that in the atherosclerotic lesions extracted from humans, there are also helical crystals. And beyond that, we do believe now that we also understand how these helical crystals are formed. So what can I say? This was a long and complex tour de force that we did along many years. And what I want to say is thank you, Leslie, for 50 years or almost 50 years of shared adventures in science, during which you were a constant source of inspiration that extended well beyond crystals. Thank you very much.